dear students, we will talk about the application of Schrodinger wave equation to particle in a one dimensional box. So, our problem is now the model system. The model system is particle in a one dimensional box, which we also say infinite potential wave. Okay. We talked about this in the previous class and we will talk about this again, because this is the most important problem as far as the basics of quantum chemistry is concerned. You must know and you must understand it properly. Particle is moving on x axis, okay, and you have potential energy outside this boundary is infinity. Inside this wall, the potential energy is 0. So, what you can write? You can write the Schrodinger wave equation, and Schrodinger wave equation will be d square psi by dx square 8 pi square m by h square E minus v psi is equal to 0. Remember, we did Hamiltonian, I have written Hamiltonian in the last class, now I am writing like this one, anything you can write, it is the same thing. Okay. So, since v is equal to 0, potential energy v is equal to 0, so your equation will be d square psi by dx square plus 8 pi square m by h square E psi is equal to 0. Okay. If we assume if 8 pi square m by h square into E I write as kappa, then we can write d square psi by dx square plus kappa square psi is equal to 0. It is the same equation which we did in the previous class. So, now you have d square psi by dx square plus kappa square psi is equal to 0. We can write a solution, general solution. I write it a sin kx plus b cos kx. We have written the exponential solution in the previous class. Now, it is a trigonometric solution. That one is convertible to another, through which formula you know Euler's theorem. Okay, you can convert one into another. So, a sin kx plus b cos kx. So, take the differential of this. What do you get? You get a k cos kx plus b, and it is minus sin kx. So, k minus k sin kx. Then take another differentiation, and again we will have a again k with a minus sign. So, minus k square sin kx, and then you again k with a plus sign. So, it will be again minus k square cos kx. So, you can bring minus k square this side, and what you have? A sin kx plus b cos kx. So, you have k square psi. So, this differentiation tells you that one of the possible solution of this equation is a sin kx plus b cos kx. In contrast to the previous one, where I said you that we do not have any boundary condition, here we have a boundary condition, that the particle in a one dimensional box can move between the limit x is equal to 0 to x is equal to a. Means, and here there is a drastic change in the potential also, from v is equal to 0 to v is equal to infinity, and here also v is equal to 0 to v is equal to infinity. It means that at this point the wave function will be should be 0, and at this point also the wave function should be 0. There is no point beyond this point or beyond this point, x is equal to 0 and x is equal to a, the particle cannot exist because the potential energy is infinity. Okay. So, psi will be 0, and if psi is 0, then we will apply this boundary condition to the solution of Schrodinger wave equation, and solution of the Schrodinger wave equation is psi is equal to a sin kappa x plus b cos kappa x. So, applying boundary condition, we say that psi is equal to 0 at x is equal to 0. So, the equation will change, psi is equal to 0 a sin k into 0 plus b cos k into 0, and what does it mean? Sin 0 0 and cos 0 1. So, you have b is equal to 0, and if b becomes equal to 0, then your psi reduces to a sin kappa x, because b is equal to 0 now. Second boundary condition is that psi is equal to 0 at x is equal to a also. So, put these values in this equation. So, psi is equal to 0 a sin k a, x is now a. Okay. Now, this equation is true if a is equal to 0 or sin k is equal to 0, sin kappa is equal to 0. Okay. If I say a is equal to 0, then b was already 0, a is also 0, the wave function itself will become 0 and the particle does not exist. Okay. So, that will give you a redundant solution, no solution at all. So, therefore, sin k a is equal to 0, and you know from trigonometry that sin n pi is always 0. Okay. It means k a should be equal to n pi k. K a should be equal to n pi k, and k should be equal to n pi upon a. And if you use this value and you rewrite this equation, then your psi will be equal to a sin k is equal to n pi upon a into x. So, we have got a wave function for the particle in a one dimensional box or infinite potential well. Okay. Now, this wave function is not normalized. You need to normalize it. Means this value, the value of this of a should be such that psi dx integrated from 0 to a should be equal to 1. That is the normalization condition that should fulfill normalization condition. So, whenever we apply Schrodinger wave equation to any system, we first find out the wave function and then we normalize the wave function. I said you it is essential to normalize the wave function because you want to ensure that your particle is present within the boundary. If it is not present within the boundary, then we cannot talk about that system in quantum mechanics. Okay. And I gave you the example also that normalization is important because if the particle is not there, which property you are going to determine. Okay. So, we will try to normalize these wave functions, and wave function is psi is equal to a sin n pi x upon a. And what is the normalization condition? normalization condition is that psi star dx, if we are writing from for one dimension, this should be equal to 1. Okay. And since we do not have a real imaginary function, real function, so this psi will be also be psi star will also be psi. And what is your minus infinity here? Your system starts from 0 point, and what is the plus infinity? It is a. So the limit of the integral will be 0 to a, and your function is a sine n pi x upon a into dx. Sorry, and then again the next function is a sine n pi x upon a into dx. So what we can write is a square from 0 to a, and then sine square n pi x upon a into dx, and this should be equal to 1, this should be equal to 1. This you have to find out. Okay. And sine square x is 1 minus cos 2x divided by 2. Okay. So you can what you can write is a square from integral from 0 to a, and this you can bring this side, and it will be 1 minus cos 2 n pi x upon a into dx is equal to 1. Okay. This you have to integrate. So try to integrate this. A square by 2. Your first integral is dx between 0 to a minus second integral is 0 to a cos 2 n pi x upon a into dx. Okay. Then sorry, not n pi. Yes, cos n pi divided by x. Okay. Okay. Okay, fine. So this is equal to 1. Now the integral of this will be how much? A square by 2. Integral of this will be a. I will write a minus 0 minus integral of this will be how much? It will be a divided by 2 n pi sine 2 n pi x upon a. Okay, between 0 to a. Okay. If you put the upper limit a, then x in place of x, then a and a will go, it will be sine 2 n pi, and again it will be 0. If you put this lower limit 0, then again it is sine 0, so it will become 0. So this term, this whole term will be equal to 0, and now you have a square divided by 2, a square divided by 2 into a is equal to 1. So it will be a will be root under 2 divided by a. Okay. This is called normalization constant. Okay. On the previous thing, one thing which I wanted to tell you is that here you have Ka is equal to n pi. So that sine Ka becomes equal to sine n pi, and both give you 0 value. This also gives you 0 value, and this also gives you 0, then only you can do it. And for that, what should be the n value? N value will be 1, 2, 3, 4 and so on. Okay. So for this is called quantum number of particle in 1D box. Okay. you see this is your function. If n is equal to 0, if you put y sine 0 is also equal to, this is valid, sine 0 is 0 and sine n pi is also 0. Okay. If you put n is equal to 0 value, then the whole function becomes 0, and this we do not want. That is why n is either 1, 2, 3, 4. Okay. So, the normalized wave function, now I will see normalized wave function, I will give a symbol n here, and I will write normalized wave function for particle in a one dimensional box is root 2 by a sine n pi x upon a, and where n is equal to 1, 2, 3, 4 and so on. Okay. So, this is the, what we have determined is the normalized wave function. What about the energy of the system? Energy of the system you get from here. Look at this equation, that we have taken 8 pi a square m e divided by h square is equal to k square. Let us see. What we have, 8 pi a square m e divided by h square is equal to kappa square. And what is kappa? See, if you go back and you see, kappa is equal to n pi by a. Okay. So, you put these values, n square pi square divided by a square. So, pi square and pi square will go. Okay. E is there. So, E will be equal to n square h square divided by 8 m a square. Okay. And where n is equal to 1, 2, 3 and 4. So, you can calculate the first energy E1, that will be h square divided by 8 m a square, and you will have a corresponding wave function root 2 by a sine n is equal to 1. So, pi x divided by a. You have the second energy level for possible E2, which will be 4 h square divided by 8 m a square with a wave function root 2 by a sine 2 pi x upon a. You have a third energy level E3, that will be 9 h square divided by 8 m a square, and energy will be root 2 by a sine 3 pi x upon a, and so on. E4 you can write 16 h square divided by 8 m a square, and psi 4 will be root 2 by a sine 4 pi x upon a. So, each of these wave function characterize one energy level. Okay. So, we say this to be the lowest energy, ground state, and so quantum state 1. Then this is your first excited state, quantum state 2, second excited state, quantum state 3, and so on. Third excited state, quantum state 4. So, the lowest energy state is called the ground state energy. So, we have for a particular one dimensional box, we have different energy values, and we have for each energy state, for each quantum state, we have different wave functions, and that is the normalized wave functions. Okay, for a particle confined within the area of 0 to a. Let us see what will be the shape of the wave functions if you want to draw. So, start with the ground state wave functions. The ground state wave function is psi 1 and the normalized wave function is root 2 by a sin pi x upon a. If I say your particle in a one dimensional box is like this one from 0 to a. So, if we with this equation if we try to find out the value of wave function psi 1 at different point from 0 to a, we can write at x is equal to 0, what will be the psi 1? Psi 1 will be root 2 by a sin pi multiplied by 0 divided by a. So, sin 0 will be 0 and the wave function will be 0. At x is equal to a by 2, before a by 2, at x is equal to a, what will be psi 1? Root 2 by a, and root 2 by a will be sin pi a divided by a, x will be a. So, this will go and again sin pi is 0, so it will be 0. What will be the wave function at x is equal to a by 2? So, what you can write psi 1 root 2 by a sin pi by a into this is a by 2. So, it will be sin pi by 2 and that will be equal to 1. Okay, sin pi by 2 will be equal to 1. So, your psi 1 will become equal to root 2 by a. So, what you observe is that wave function here is 0, wave function here is 0, but in the middle at a by 2 the wave function has a positive value. So, if you want to draw this, you can draw a wave function shape like this one very easily. Okay? And that is what you do for other wave functions also. Say for example, psi 2. For psi 2, you have root 2 by a sin 2 pi x upon a. And then if you calculate at x is equal to 0, psi 2 will be 0. At x is equal to a, psi 2 will be 0 because it will be sin 2 pi. At x is equal to a by 2, and you look at this one a by 2. So, again it will be 0, psi 2 will be 0. Okay. At x is equal to a by 4, psi 2 will be root 2 by a, and x is equal to 3a by 4, psi 2 will be minus root 2 by a. Okay. And if you plot this in a one dimensional box, so the lowest wave function was this one. The second wave function will be at x is equal to 0, it is 0, at x a by 2 also it is 0, and at a also it is 0, but at a by 4 it is positive, and at 3a by 4 it is negative. So, you plot it like this one. Okay. So, you see we have one point here in between the particle in one dimensional at the middle of the box, where you have wave function 0 at a by 2. If the energy is E2, if you go for first excited state, then what you say that at one of the point in between the box or at the middle of the box, the wave function is 0, and wave function 0 means particle will not exist here. Okay. First, let us try for another function psi 3, and psi 3 is what? Root 2 by a sin 3 pi x upon a. And if you find out the values here, at x is equal to 0, psi 3 will be 0. At x is equal to a, psi 3 will be 0. At x is equal to a by 3, psi 3 will be 0. And at x is equal to a by 6, psi 3 will be root 2 by a. And rest of the value you can calculate. And if you do this, you look at this, how does it appears? one first wave function, second wave function, A, and A by 3 I have determined. So, cut it into 3 parts, A by 3. So, it will be like, it will be like this one. Okay. So, we have 3 different parts. Here you have a positive value root 2 by A, here you have negative value minus root 2 by A, here you will get positive value root 2 by A. So, these are the points, this, and these are the points where wave function psi is 0, and these are called nodes. Okay. And so, we can give a symbol for the wave function also. It is all positive here, all positive here. Here we have a positive and a positive value, a negative value, and again a positive value. So, this is the plot of the wave function for particle in a one dimensional box. And if you go for the plot of square of the wave function, which gives you the probability side by side, if you plot, like this one. Okay. So, positive, negative, positive, positive, negative, positive. If you plot the probability, then it is simply a square of the wave function. So, you will not have a negative area, it will be all positive. A square of negative will be positive. Okay. So, this is the probability, this is the wave function for 1D box model. And what does this tells you? This tells you that if you have a one dimensional box in which the particle is moving, and if you place a particle, then with an energy equal to E2, E1, E3, psi 1, psi 2, psi 3, this is psi 1, psi 2, psi 3, again E1, E2 and E3. So, if you place a particle like this, then particle has a probability of being found at this point, particle has a probability that it will be found here, and see it is a one dimensional box. So, particle will not go in the y direction, it has to move on this line only, on the x direction, because we are talking about one dimensional problem. Okay. So, what we say that particle can move, can go from this point to this point without touching this point on this axis, which you cannot think of in the classical mechanics. In the classical mechanics, if the particle is moving on a straight line, then it will touch all the points of this line if it has to go from one end to another end. But here we say that no, there is a probability that particle can be found here, there is a probability that particle can be found here, but in between at this point at a divided by 2, the probability is 0, because the wave function itself is 0, and if the wave function is 0, then the probability has to be 0, because a square of the wave function is probability. Okay. So, what you say is that particle can move from this point to this point without going in the y direction and without touching this x point, this point x, where the probability is 0. So we say that quantum mechanical results and the behavior of their small molecules, small electronic systems are very weird. We cannot comprehend it from the daily experience, but mathematically we have proved that this is the wave function and this is the probability. So, particle can move on this line, can go from this P point to Q point without touching X point. Okay. which we cannot comprehend, but mathematically we have proved it. Okay. So, this was the particle in a one dimensional box model. Okay. And here we have taken a particle in a one dimensional box where we have the potential outside the box is infinity on both sides, and inside the potential is 0. So, this is called infinite potential well from 0 to A. We will talk about different variations of this potential well problems in the next class onwards. Okay, thank you.